In this video, we will discuss the stress analysis for combined loading conditions. So what is a combined loading? Well, in engineering, structural elements are generally under combined loadings. For example, if you have a beam and you draw the shear force and the bending moment diagram, you see that in this beam, which is under the effect of support forces and external forces, in this beam, each section has a different combination of shear force and bending moments. So in this section, well, shear and bending is effective. So for the stress analysis, we have to take the critical sections first, and in these sections we have to consider all loadings and calculate the stress distribution. What are the loadings which we have already discussed up to now? These are the basic loading types. Well, axial loading, tension, compression, shear forces and developed shear stresses, bending moments and bending stresses, and torsion. So in a combined loading, two or more of these loadings will be acting together. And so when we discuss the analysis in combined loading conditions, well, it means actually this analysis will cover all our knowledge about the basic loading types. So what are the basic loading types? Let us remember, this is the normal force. Well, in this case, we will have a uniform distribution of normal stress, and you can calculate it force divided by the area. In shear, well, we have this shear formula. And if you have a section and you have a shear load, well, we know that the stress distribution is not uniform. On both upper and lower surface, there's zero, and maximum on the neutral axis. And for other sections, we have to use this formula. Bending moment, well, causes normal stresses due to bending. And this distribution is, as we remember, also not uniform. On the neutral axis, the stress is zero. On the upper and lower surfaces, we have maximum stresses, but their signs are opposite. Next, when we have a torsional moment, well, the shear stress which is caused by torsional moment is so that it's zero in the middle, maximum on the surface, and the distribution is a linear distribution throughout the section. Okay, these are the basic loading types we're going to consider in our combined loadings. In combined loading, what we do is we have to calculate the stresses and strains caused by each single load separately, and then we will have to apply superposition for their joint effect. So it's not too complicated, so we have to consider each loading separately, calculate the stress distribution, and then sum their effects by superposition. In a stress analysis for combined loading, we have the following steps. First, we have to determine the critical sections. Well, each structural element has infinite number of sections, and so we cannot make our analysis for each section. First, we have to determine the critical sections. For this, we can use the shear force diagrams, bending moment diagrams, and these diagrams show me in which sections the loadings are maximum. If we have the internal forces and the moments acting in this section, so we have the second step to find the stress distribution for each of these loadings separately. For example, if you have a normal force, well, there will be a uniform normal stress distribution. Well, if you have a torque, for example, well, the shear stress distribution will be, let's say, linear, starting with 0 in the middle and having its maximum on the surface. So we have to find the stress distributions for each separately, and for the critical points in the section, we have to find the joint effect of these loadings by superposition of the stresses in that point. When you want to superpose stresses, you can only add the same type and stress in the same direction. So you cannot add a normal with a shear stress or stresses in, let's say, different directions. So we have to consider this during the superposition. And we have also to be sure that we are still in the linear elastic zone and the shape and size changes in the structure are limited. For a point, we have seen that the stress state is given by 9 components. 3 of them are normal stresses and 6 of them are shear stresses. And during the superposition, we determine these components. Well, for a normal stress, we remember that the index will show me the direction of the stress. For a shear stress, the first index gives you the direction of the normal of the plane, and the second gives me the direction of the stress itself. Well, let's take a section, and in this section, let's put all internal forces and moments and try to find the developed stresses. Let's start with the forces. What type of forces can be effective? Well, if X, Y, and Z are my coordinate axis, the first is the normal force. The normal force is in the Y direction, as you see over here, and this normal force will cause a normal stress. This stress is uniform and is at each point of the section N over A. There are also shear forces. Well, we have 2 components of the shear force, and each component will cause a shear stress. Let's take the component Z. So this will cause a shear stress tau YZ. Y is the normal of this section, and Z is the direction of the shear force. Where is tau YZ? This is tau YZ. In order to calculate the shear force in the Z direction, I have to use VZ. And since for such a shearing, the neutral axis is the x-axis, so I have to do my calculation with the area moment of inertia, IXX. So the same you can do also for YX. This time you will have tau YX, and that is this formula. And this time your neutral axis is in this direction, and this is the Z, and so you have to use the IZZ. Okay, what did we find out? Well, when you have forces, these forces may be normal or shear, and each component will cause, the normal forces will cause normal stresses, and the shear forces will cause shear stresses. And you have to consider also the normal of the plane and the direction of the shear stress in order to find the indices of the shear force. Next, the moments. There are mx, my, and mz. These are the possible moments. Well, the blue one is perpendicular to the plane. It causes a torsional loading, and we call it also a torque, and the torsion formula is this blue formula, and it has a shear distribution in the plane, 0 in the middle, maximum shear on the surface. Besides, we have bending moments. Let's consider the bending moment mx. Mx causes a bending around the x-axis, and imagine, well, we have a deformation like this. So on the top we will have positive, on the bottom surface we will have a negative, and 0 in the middle. So in this case we will have again a distribution, and positive, negative, 0 on the neutral axis. Where is my neutral axis? It is this axis. So, and the cos sigma is in the y direction. So we will have, for example, positive sigmas in this direction. So we can calculate with this formula and take mx, and since my neutral axis is the x-axis, I have to use as the moment of inertia Ixx. You can do the same also for mz. In this case, we have a torsion around the z-axis. Well, the moment of inertia and the bending moment we have to use are these values. Okay, bending moments, when they are torques, they cause shear, and when they are bending, then they cause normal stresses. Well, here you have everything all together, forces and moments. Forces, normal, shear, torque, and bending moments, and these are the stresses caused. You see, these stresses will create a stress state, and this is what we're going to find in a stress analysis by superposition. So as you see, we have our forces and moments, and these forces and moments cause normal and shear stresses, and we are going to make a superposition for this surface. Let's consider the normal stresses. Well, the normal stress, which is perpendicular to the surface, should be in the y direction. The sigma y values are over here, and over here. There are 3 normal stresses caused, one by normal force, the other 2 by bending. So we add them together. This is superposition, same type of stress and same direction, and we find the sigma y value. Okay, next we have to consider the shear stresses. Well, the shear stress in this direction, that is yx. Y means that the normal of the plane is y, x is the direction, so this is caused by this shear, and we know that a torque, when you apply a torque, you will have on the surfaces all over on the surface you will have a shear stress. So you can take, for example, to add with this one, well, the one in the same direction, and you find what you find the tau yx value. Well, the same you apply tau yz, and that is the shear stress caused by the tau yz with this formula, caused by yz. This is your shear force, and we know somewhere on the surface we will also have a shear stress due to torsion, which is in the same direction, and so we will find also tau yz. This is how, when you know the forces and moment, how you determine the stresses caused by these forces and moments, and how you add them together by superposition, and how you find the stress state in a point. Well, here we have a simple problem. Well, here we have a clamp. The clamping force acting is, these forces are 400 newtons. Determine the stresses in points A, B, and C. So these are points A, B, and this is the point C. So the sections are given. So we do not have to find the critical sections or so. So, well, the sections are given. First, we take this section. What we do is we first cut and try to find out the internal stresses and moment in this section. Well, you see I made a cut and have taken this part and drawn the free body diagram. I know the force, the clamping force which is acting, and in the section AB, what internal forces and moments are acting. For this free body diagram, I write down the equilibrium equations. So you find out when you write sigma Fy equals to 0 and sigma m equals to 0, that in this section N is 400 and m is 40,000 Newton millimeter. Okay, now I know that I have a normal force and a bending moment. Well, let's take the point A. In point A, in this section, I have, let's take this point, I have a normal force and a bending moment. So the normal force will cause force divided by the area, a positive sigma, and the bending moment, since it's on the left side, it will cause a negative compression. The formula is my over I. M is my bending moment. This is the distance from the this is my neutral axis. This distance is 10 millimeters. Why? Because as you see on the section, this section is 20 millimeters. If this is my neutral axis, so this distance is 10. So 1 over 12, 10 to the 20, 10 times 20 to the third power gives you the superposed stress in point A. What did I do? I have calculated the sigma due to normal force. I have calculated the sigma due to bending. One is positive, the other one is negative. By calculation of the separate forces and by adding them together, superposition, I have found the stress in point A as minus 58. If you do the same for point B, well, you know the stress due to normal force is uniform all over in the section, but on the right side in point B, in point A I had negative, in point B I have positive and tensile stresses, moment of inertias, and all other stuff is the same. This time, well, this is plus and this is also plus, so the superpositions gives me that the stress is 62. So I have determined sigma A and sigma B. There are no shear forces in this section. There are no torsion in this section. So we have only one normal force and one bending moment. So the analysis was not too complicated. Well, next we have to consider this section. I cut here and take this side or this part, draw the free body diagram. Now my internal forces are a moment, bending, and now it is a shear, and shear is a force acting in the plane. So let's try to find the force or the stresses in point C. In point C, well, if we draw this section in point C, it is something like this. That is 20, that is 10. My point C is here, and this is the neutral axis. And we know that the force 400 is acting like that. And we also know that when you have a shear stress, it's maximum on the neutral axis, it's 0 on both surfaces. So since the point Z is on the surface, the shear stress due to the shear force will be 0. So that was very easy. So in point C, the effect of V is 0. Now we take M. M will cause a compression. So this is my moment. This is again the distance from the neutral axis, and this is again my moment of inertia, negative compression minus 24, and that is also not very complicated to find. Another problem: find the stresses in point A, B, and C which are in section AA. Section dimensions are B and H. B is this dimension and H is this dimension. Here again, the critical section, or the section where they want me to do the analysis, is given. So all I have to do is make a cut and find the internal forces and moments in the section. So the first thing I do is to find the support forces, and you can do it by equilibrium. These are your support forces. You cut here. Well, the right side is more complicated. Let's take the left side, and this is the left side you have to consider. You take this free body diagram and you try to find the forces and moments in this section. So if you like the equilibriums, you find that N is minus 72. Why minus? Compression. V is 36, M is 288. So I have a section like this where I have a negative normal force, a V and M. So question is, what are the stresses in points A, B, and C? First, we consider the normal force. Minus 72. Force divided by the area gives you minus 0.6. That is a stress distribution like this. You see uniform everywhere. The normal stress is minus 0.6. Next, shear force. We have a shear force 36, okay, acting downwards, okay. We know that the shear force distribution, shear stress distribution is not uniform. It's maximum on the neutral axis. Its value is, for rectangular section, you can calculate V over A. V over A, that's the average shear stress, times 1.5 gives you the maximum value. Okay, so I have the stress distribution due to normal force. I have the stress distribution due to shear. Next, bending. Well, this is my bending moment. It causes negative upper, positive lower. The maximum value are moment, the distance from the neutral axis, and this is the moment of inertia, 1 over 12 bh cube. Well, you see I have 3 loadings, 1 normal, 1 shear and 1 bending, and they have 3 different stress distributions. So I have to make a superposition. This one plus this one plus this one is my superposition. If I take point A, this point, as sigma, this is sigma, this is tau, and this is sigma. So shear stress in point A at this point is 0. And in B, shear stress is 0.45. In C over here, shear is 0. What about the sigmas? For A, I have minus 0.6, minus 24, minus 24.6. And for point B, where is this? For point C, excuse me. For point C, I have minus 0.6 plus 26. This time it's plus. So I have the superposed value. And for point B, you see, I have only this. Here, sigma is 0. So that is only minus 0.6. So, in summary, what did I do? I first found the forces. They were a normal force, a shear force, and the bending moment. Then I have found the stress distribution separately, and then for the points I'm interested in, I have made the superposition and found the stress state. Okay, well, that is our last problem, well, which is in 3 dimensions. So when we have a solid bended rod, so these are the applied forces, find the stresses in points A and B. Okay, this is the section which is critical. So this section is a round section. Point A is here, point B is here. When you draw the axis in 2 dimensions, it's something like this, okay? So I have to find the moments and the forces in this section. When you cut, you see, you have to find each force one by one. Well, if you look at the whole drawing, you may think, well, it's too complicated, but it is not. After cutting through A and B, the internal loadings can be calculated. First, calculate, well, the normal force. Well, if this is your section, calculate first the normal force. Well, if you write sigma Fz equal to zero, there is only this force and this force. So it means that N is 500 and negative. Why? Because it's compression. So when you want to, for example, find the force in this direction, let's call it Fy. Is there any external force in the y direction? No. Sigma Fy equals to 0 gives you that Vy is the shear force in the y direction is 0 because there is no external load, but in the x direction, in this direction, if you write sigma Fx equal to 0, you find that Vx is 1000. So what did we do? Well, we easily found the values of the forces. Well, we have, as you see, one normal force. This is not present, and one shear force in the x direction. So what about the moment? Let's take mx. Mx is, this is my axis. I have to rotate around this axis, okay? Well, which external force causes? You see that 500, and this is the moment arm, will cause a rotation like this. And in order to find an equilibrium in this section, there must be a bending force mx in this direction. So when you apply the right-hand rule, well, this is a positive direction. So you see that 500 times 0.1 meter gives you 50 Newton meter as the mx value. Okay, let's clear everything and go to the next moment. The next moment is my. Well, rotation around this axis. Well, this will go through the axis, so there is no moment arm. This one causes a rotation. So this is the arm that is 200, and this is the force, and you find the my value. You see, that is also finished. The next one is to find the torque, that is the mz, which is the torque. So this force tries to rotate the section around z, and in order to an equilibrium, well, the force will be 1000 times this 0.1 meter, and this is your torque. So the question was, find the stresses in point AB. Step number 1, we took the section going through AB, and for this section I have determined with the help of the equilibrium equations the forces, shear and normal forces, and the bending and the torsional moments, and now I have their values. The next is to calculate the stress distribution for each of these forces. So first we discuss the normal force. Don't consider these, don't look at them, just take this, Okay, the force acting is minus 500. Well, this is the area, and now you have a stress distribution minus 1.59. Blue, because I have made the sigmas all blue and the tau values all yellow. So that is done. Next is the bending moments. Here I have a bending moment mx. Mx means a bending around this axis, and I have my. My means bending around this axis. On the axis x, it's 0. On this axis, this is 0, and I have to calculate the values of the stresses caused by bending. So I know that mx is 50, my is 200, and the distance is all 10 because the maximum stresses are on the surface, and this is the moment of inertia. So as you see, this value is 63 and this value is 244, and now I can draw the stress distribution for the bending moments as shown in the figure. Forget this and forget this. So we are making analysis for bending. You see over here I have plus, minus, so you have to check the directions, and on this surface it's minus 200, on this surface it's plus 254. These are also done. Next, we forget the normals and look at the shear. Shear first due to torque. I have a torque 100, and all over on the surface I can calculate with the formula 100. This is the polar moment of inertia, this is the radius, and all over we have a 63.7 shear stress. And the last one, that is the shear force. Shear force is acting like this, and it has maximum in this direction, in the YY direction. So on the YY axis, it's the neutral axis, 0 over here is 0 over here. And you see, I have to calculate when you have a circular section, when you calculate V over A as the average tau, you can find the maximum, this maximum, tau max, as 4 over 3. So this is the maximum tau. You don't have to use the complicated formula TQIT formula. For sections, when you have a rectangular section, well, the maximum is V over A 1.5. When you have a circular section, you have 4.3 V over A. So this is what I did over here, and I have found that the maximum is 4.25. Okay, now I have everything. So I had a critical section. I found that there are normal and shear forces, there are bending moments and torques on the surface. For each loading, I have calculated separately the stresses and their distribution. And now my last step is to find the stress states for points A and B with the help of superposition. So in superposition, we have to add stresses of the same type and in the same direction. Okay, so let's start with sigma. Sigma is the normal force, and sigma is the normal stress, and the normal force causes also sigma. In our case, it is minus 1.59. And as you see, this stress is negative for point A, and it is the same for point B. Why? Because normal forces cause uniform stress distributions. So next, we go to bending moments. When you have a bending moment mx around x, it will be 0 on the neutral axis, the stress maximum on both surfaces. So for point A, the bending moment caused by mx, the bending stress caused by mx is 0, and the bending moment stress in B is, as you see over here, minus 63. If you take the bending moment my, in this case your neutral axis is here. For A, you have now positive maximum, that means this value, and for B, since it is on the neutral axis, you have 0. So first we have calculated in this section the stress, the normal stresses for point A and for point B. Okay, superposition, that was not too complicated. Now we try to make superposition for the shear stresses, and we may have shear stresses in which directions? We may have shear stresses in this direction. This is positive tau zx, and we may have shear stresses in this direction. This is tau zy. What does z means? It shows me that the normal of the surface is z and x is its direction. So let's take the torque. We know that a torque causes maximum shear stresses all over on the surface. So what does it mean? It means that it has, since A and B are both on the surface, they will have the same value, but here, well, this is positive, this one is negative. So for A, I have, what do I have? For A, I have negative tau zy, because it's in this direction, it's positive, I have a negative stress. So for B, well, I have positive. For B, I have positive zx. So you see, this is the same value. That's the same value. Well, these are caused by torque. So now let's come to shear. We know that when you have a shear force like this, on the surfaces, these values are 0, and in the middle or on the neutral axis, the value is maximum. So this stress is a Zx stress, and in point B, the Zx value is, as we have calculated for the shear, 4.25 positive. And if you look for point A lies on the surface. So point A has actually nothing. So we will have, let's say, +0. And in the other direction, there's actually no stress at all. So after having done this superposition, let us have a look. Well, the answer to this problem is, in point A, we have sigma plus 253, tau zy minus 63, and tau zx 0. Well, the same you can give also for point B. In summary, well, the procedure for combined loading analysis: find the critical section, find the normal shear forces and the bending and torsional components of moments. That's the number one. That's important. But all these forces should act through the centroid. Well, otherwise there will be some bending moments created and our formulas will not be valid. All the forces should act at the centroid, and the moments should be also computed about the centroidal axis. So if you have this, next step is calculate the distribution of the stress components associated with each internal loading separately. Normal, shear, bending, torsion separately. And if you have these, use the principle of superposition and determine the resultant normal stress and shear components for the points on the section. In the same section, there will be different points, and since the distribution is not uniform for all components, so each point will have a different stress state. Okay, that was our video about how to make a stress analysis for combined loadings, and thank you for listening.